Welcome back to my channel. Today you will have the opportunity to feast your eyes on this marvel of engineering, this beautiful example of mechanical perfection, this well-oiled machine achieving its goal with grace. And it's locked up again. So today we'll have a look at 3D printing this cool sign that changes its text between open and closed, using the magic of 3D printing and gears. And if you stick till the end, you'll learn the basic knowledge behind meshing of spur gears and why I think it's a terrible idea to 3D print gears this small. But first, let's talk about Schrodinger's sign over here and how it works, and most importantly, how to design it. I first saw this sign a few years ago and I thought it was pretty interesting how it uses clever letter design and advanced kinematics to change the text and rotate the letters. We start off by looking at the letter design that makes all of this possible. We have the word open and we need to convert it to closed, and it looks like we're missing a few letters. The simple one is the letter N that can be rotated to double as an S. Second and most interesting one is P. It can be rotated and double as a D. The shape of the letter can also hide behind it the letters C and L. So looking closely at this P, we are able to hide the C and L behind it, like so. The setup we will go with is this: two identical gears that mesh together, and on the right gear we add two planetary gears that spin at different ratios around the fixed central gear to flip the N and E letters. Then we attach the right letters to the right gears, figure out which letters go where and how to fix them, and hopefully we achieve a motion like this. Pretty simple, right? I will begin modeling this in CAD and simulate it to check if it works. But first, let's go through a little bit of theory about gears. Why do we generally use gears? Well, we use gears for two reasons: to increase speed or to increase torque, and each one is achieved through the expense of the other. If we have two identical gears meshing together like this in our example, there is no change in speed or torque. The gears will just have opposite speed direction. But if, let's say, we make the drive gear larger, and we do this by doubling the number of the teeth, then the other gear will spin twice as fast but with half the torque. And we say that this set of gear has a ratio of 0.5. The ratio is calculated by dividing the number of teeth on the driven gear by the number of teeth on the drive gear. You can daisy chain gears like this, and the gear ratio of the entire assembly is just the product of all individual ratios. But can you have just any gear meshed together like this? Well, yes, if they have the same module. Gears are defined generally by two parameters, and the rest of the complex geometry can be calculated using those two. One is the number of teeth, and second is the module. The module is the ratio between the reference diameter and the number of teeth. The reference diameter of the gear is the diameter at which the teeth from the two gears touch, and generally speaking, the larger the module, the bulkier the gear. Companies usually standardize modules to ensure the different gears from different manufacturers are able to mesh together. Using these two input parameters, we can calculate all the geometry of the gear. I'm not going to go through them now, but you can find the formulas online, and calculating them is pretty straightforward. You just have to go through them one by one and you'll have all the required values. One thing to note is the tooth profile. While we get the general size of the tooth from the previous formula, we don't get the curvature. If you didn't know, this curve is not an arc or a random curve. It's a very specific curve called an involute curve. An involute is the curve described by a line rolling without friction on a circle. Why is this important? Well, it could work with just an arc. However, using this specific type of curve, we guarantee that there is no sliding friction between the teeth when they mesh. Instead, they just roll off each other, thus greatly reducing wear and tear on the gear. But enough about theory and formulas, let's start modeling this. I will first draw the letters, since they will be a little bit tricky to get right. Using a simple spline, I sketch the outline without any regard for scale at this moment. Next, I will create the gears. Luckily, I don't have to create them by scratch, and this is really lucky, since doing so would have taken a huge amount of time. I have saved some CAD files from a previous video where I designed a set of parameterized gears, where I just input the number of teeth and module as parameters, and the geometry calculates and updates automatically along with the correct involute curve. You can check this out. I will link the video in the description below. So I create and position all the gears by duplicating the file I have saved and changing the parameters. The distance between them is also calculated inside the gear as a parameter, so I make sure I use that. The planetary gears for E and N need to fit inside the big gear, and the N gear needs to spin multiple times. Once I have the gear set up, I add some weight reduction holes. This is not actually required while 3D printing, since it'll increase the print time and the benefits will be marginal at best, because we're only using 30% infill, but I just want to make them look good. Now just a quick design for the support, and begin adding some thickness to our letters, and it's ready for a quick kinematic simulation to ensure that nothing clashes while in motion. Again, I have covered how to do this in a previous video, which I'll link in the description. So I'll go a little bit quickly now, but generally speaking, we just create a new mechanism and joints between the parts, ensure that we fix all degrees of freedom. And we see that we made a miscalculation while designing the end gear. We need to adjust the number of teeth on that and run the simulation again and see that now it looks good. Finish up by putting some caps and pins in the design and polishing the leathers with chamfers and attachment to the gears. Also, I've redesigned the back plate to look a little bit better because I didn't really like it. And it's all done. We can start printing now. I'm going to split this into 3 prints. I import everything in Cura, pack it neatly to save on travel time during print, and I do this for all prints. Cross my fingers and hope nothing goes horribly wrong, because this is going to take a while. Actually, the single thing that bothers me about 3D printing is waiting around 1 day to finish a 200-gram print. Something does go horribly wrong with the pins that I printed horizontally, but luckily they did not ruin the whole print and I just had to print them again. The gears are a bit sticky, so I sprayed them with some alcohol. Retrospectively, I should have added a small chamfer at the bottom to help with removing them. But generally, I'm pretty happy with how it turned out. What I generally do now is take all the parts and clean them up a bit. Remove any strings from the printing process and most importantly, remove the supports if I used any. After I'm reasonably happy with how the parts look, I need to do a quick fit check. As we know, physical parts are not always an exact match for CAD files, and sometimes the dimensions can be really off. I check and see that in some cases the holes are a bit small, and in other cases, like the leathers connecting to the gears, they are too big, or rather the pins are too small. In any case, I will have to glue them together to assemble them. I use sanding papers on the pins to smooth them out, and I drill the holes of the gears to make them fit properly, and remove any excess plastic lodged in places it shouldn't be. And after I'm happy, they're ready to be spray painted. The process is really quick. I just use some spray cans outside on a piece of cardboard. After they're all dried up, I take them back inside to try to assemble them again. And of course, after a first try, I realized I made another mistake. I did not account for the thickness of the pin cap for the 2 planetary gears, so I quickly grind the support down locally. After this final tweak, I start assembling the pieces one by one, starting from the support, then with the gears, gluing the leathers, realizing that the pins are too small to work, ended up gluing them too, and all around having a hard time getting my chubby fingers around such small parts. But finally, after hours of painful fiddling, it's ready. I try it out and see that the components work as intended, although the tolerances on the gears are total rubbish, which brings me to my final point. There is no way that the dimensions on the actual parts are going to be exactly like in CAD, and while in theory we should only get about plus minus 0.1 millimeters on this printer, there are many things that are going to affect the print, and we are realistically looking at plus minus 0.5, and considering the teeth on the small gears are just 2.5 millimeter thick, that is 1/5 of the thickness. Imagine buying a car that is half a meter longer only on the left side. That wouldn't be really great with it. So, if I truly wanted a robust design, I would not 3D print gears that are this small. It's just not a good idea for a high precision component like a gear. Yes, there are things you can still do to improve it, but I don't see how the results would be great. But here we are at the end. I end up having this beautiful sign that kind of works. It ended up taking a lot more time than I expected, but I'm happy it all worked out. So don't forget to leave a like and subscribe to my channel if you want to see more content like this. Until next time.